Hey guys, welcome back to chapter 19. We just finished with attack with nitrogen nucleophiles, and now we're going to move on to hydrolysis. The reactions we did in the last few sections, we took an aldehyde or a ketone. Don't forget, I use acetone, but it could be any aldehyde or ketone here. And we could react it with, an alcohol and acid to get acetals. We also looked in the last section at the reaction with ammonia or primary amines and acid to give us an imine. You'd have an R or an H here depending on your reagents. And if we used a secondary amine, we wind up acid. We wind up with an enamine, right, with two R groups. Okay, so that was in the lectures before spring break, the last video, and where we're starting here is the reverse reactions. All three of these groups, the acetal, the imine, and the enamine are all reversible reactions. If we use H2O and acid, so we're going to use a dilute acid solution now, we can revert back to our carbonyl, to our aldehyde or our ketone. Now, in this first reaction here on Klein, right, they show you the acetal going back to the ketone, you get your alcohols back. It only happens in acid, not in base, so we're only going to focus on acidic conditions. And then you get the whole mechanism. Now, this is simply the reverse, or about the same as the reverse of forming the acetal. You have the hemiacetal intermediate, and you're going backwards. You can look at this one on your own, but since this one is already spelled out for you, I think in the notes, I'm going to go ahead and I'm going to do the hydrolysis of the imine. So let's take a look at the imine. If we have, and I'm just going to put an R group there. It could be any R group. Remember, any carbon-based group there would work. And I'm going to take my acid, and I'm just going to use HA. And there's water. Notice in Klein, instead of HA, he's using H3O+. That's also fine. Right? You just don't want to use a base. So you can either take the proton from HA or from hydronium. Just do not make hydroxide in this. Then what we're going to do is now we've got a better nucleophile. A better electrophile. And this was the second to last step when we went in the other direction and made the imine. Water is not a very strong nucleophile, so having that plus charge makes this more reactive. Now the oxygen can attack the imine carbon. We will not have 5 bonds on carbon, so push that pi bond up. We're going to have our tetrahedral intermediate. I did not plan this well, so I'm going to go to the next page here. That is going to give us water, right? We don't want to lose atoms, so we have water attached to that carbon now. We have the nitrogen with 2 R groups, and it's got a lone pair now. I'm sorry, not the 2 R groups. With a hydrogen, an R group, and a lone pair. A carbanolamine is still going to be an intermediate. We're doing the imine formation. We're just going in reverse. So what I want to do is make this neutral. All right, if I used HA or hydronium, I just want to use the conjugate base to pull off one of these protons and give those electrons back to the oxygen. All right, so I'm going to wind up with my OH and my amine attached to the same carbon, otherwise known as a carbanolamine. Now, similar to how hydroxide is not a good leaving group, This nitrogen is not a great leaving group because it would give you an amide ion, which would be very reactive. So we're going to make it into a better leaving group, just like we usually do with the hydroxide ion. We're going to protonate it so that it can leave as an amine. Right, so then we will have our OH. We will have our protonated amine over here. Our H now has a plus charge. And just like with the other reactions, we're not just going to see loss of a leaving group. We're going to form our carbonyl bond. So we're almost there. All right, we have a protonated carbonyl now. We lost our amine there. And we are, there's not a lone pair on that side. There's a plus charge, right? Because we have 3 bonds on that oxygen. So the final step is just getting our acid back, right? We used it, we got it back, we used it again, and here we get it back. Right? It's acid catalyzed hydrolysis. So then we wind up with our ketone. You will be expected to know the mechanism of the hydrolysis of the acetals. You will also be expected to know the hydrolysis of the imine, which is what we just covered. And something that you need to practice on your own now is the hydrolysis of the enamine. H2O and acid will give you your carbonyl. Let me get you started, because the main difference is going to be the first step instead of the last step. If you have an enamine, right, we are going to first need to acidify. All right, now it's not going to be the amine that picks up this proton. It's going to be the double bond, right? That was the last thing that happened when we made the enamine, was we deprotonated the carbon. So that's the first thing we're going to do in this direction. These lone pairs of electrons will come down at the same time, and it will form this iminium ion. It will form the carbon-nitrogen double bond. Now, the purpose for this is so that you have a good good electrophilic site and the water can attack. I recommend you guys finish that one on your own for practice. Right? If you look here through the slides, you see your imine hydrolysis, your enamine hydrolysis, and the mechanism is explained as well. All right, that is the hydrolysis. We are going to continue this lecture and go into 19.8 and talk about sulfur nucleophiles. This is a fairly short section. Sulfur nucleophiles work almost identically to oxygen nucleophiles. So instead of an acetal, we are going to make a thioacetal. So instead of an alcohol, we're looking at a thiol. The thiol will also need an acid catalyst, and we will add 2 SR groups to the same carbon, right? Thio meaning the sulfur derivative of the acetal. Don't get hung up on the equivalents here. Yes, with acetal and thioacetal formation, you do need 2 equivalents, but just assume you will always have enough. If you don't have enough, you're just going to get a weird mixture of products. This mechanism is analogous to acetal, right? There is nothing different except there is sulfur instead of oxygen, so I'm not going to step through that one here. You can also make a cyclic thioacetal, just like you could with the oxygens. And instead of looking at how that's useful as a protecting group, we're going to look at a third reduction. This one is called a desulfurization. Yes, I believe that's what we're going to call it. Desulfurization. This is yet another way that we can reduce a carbonyl all the way down to an alkane. In the first step, you are going to make that cyclic thioacetal, right, with the dithiol and acid. And then in the second step, you are going to use Raney nickel. This is a special kind of powdered nickel that will allow for this, this final reduction step. Just like with Wolff-Kishner, I expect you to know this is 2 steps. I expect you to know that if I ask you for just step 1, if all I showed you was this guy here, that I expect to see the cyclic thioacetal. If I put them together, right, and I have the 1 and the 2 step, right, where you've got the Raney nickel now, then I would expect you to go all the way to that final reduction. So for reductions, right, to go from a ketone to an alkane, you've got Clemenson. Clemenson is good for benzylic carbonyls. We saw that in when we did all of our aromatic chemistry. You've got Wolff-Kishner, which is done under a basic condition. And now you have desulfurization, which is done under an acidic condition, and then with Raney nickel. So it gives you options as an organic chemist to have these different reductions that work better in different conditions, because sometimes you've got things that are sensitive on other parts of your molecules, or maybe you just have certain access to certain chemicals, right? It's just always good to have more tools in your toolbox. All right, as far as the hydrogen nucleophiles go, and that is where we'll wrap this video up. The hydrogen nucleophiles are reduction reactions. So we are going to be adding bonds to hydrogen. We're going to be reducing. I do not expect you to know the mechanisms of these reactions. I do expect you to recall the rules from Organic 1, right? If you have an aldehyde or a ketone, you can use LAH followed by water, and it has to be 2 steps unless you would like to be unsafe. Or you can also use sodium borohydride and methanol. Sodium borohydride and methanol only works for aldehydes and ketones. LAH and water works for aldehydes, ketones, and other carboxylic acids and carboxylic acid derivatives. There is a mechanism here. You do not need to understand the mechanism. We will pick up in